Hi learners! Welcome to Math is Fun with Sir O. Today, I will be discussing graph theory. Today's lesson, we're going to learn weighted graphs, Hamiltonian circuit, and Dirach's theorem. Now let's go to our learning outcomes. At the end of this lesson, the learners will be able to first, know what a Hamiltonian circuit is. Second, learn the application of the Dirach's theorem to verify Hamiltonian graphs. Third, learn how to compute the value of the weighted graph. And lastly, learn how to use the greedy algorithm and edge-picking algorithm to find Hamiltonian circuit in the weighted graph. Hamiltonian circuit. A Hamiltonian circuit is a path that uses each vertex of a graph once. What is the path of a Hamiltonian circuit on the figure on the site? All we need to do is we're going to traverse at each of the vertex there on our graph, but we need to go back to the point where we have started. If you need more time to make your Hamiltonian circuit, then you can pause this video. Now let's go to our solution. We can use this Hamiltonian circuit. So we begin at vertex A, then we go to vertex B, then proceed to vertex G, vertex C, vertex D, vertex E, vertex F, and vertex A. So this circuit is an example of a Hamiltonian circuit. Do you have any more answers? Yes, of course. You can start at any point of our graph, as long as you have only traversed to each of the vertex just once, and you have to go back to the point where you have started. Hamiltonian graph. A graph that contains a Hamiltonian circuit is called Hamiltonian. So meaning, if your graph contains Hamiltonian circuit, that is considered a Hamiltonian graph. There is no known shortcut to find the optimal Hamiltonian circuit in a graph. Dirach's theorem. Dirach's theorem on Hamiltonian cycles, the statement that an n-vertex graph in which each vertex has degree at least n/2 must have a Hamiltonian cycle. Now let's consider this example. In this problem, we need to find out the route of the airplane, starting from and going back to the same airport, but not going to the same airport twice. Consider a connected graph with at least 3 vertices and no multiple edges. Let n be the number of vertices in the graph. If every vertex has a degree of at least n/2, then the graph must be Hamiltonian. Now for our solution, there are 6 vertices in the graph. So n is equal to 6. And every vertex has a degree of at least n/2. And that is equal to 6/2 and eventually equals 3. So by Dirach's theorem, the graph is Hamiltonian. This means that a graph contains a circuit that visits each vertex once and returns to the starting vertex without visiting any vertex twice. By trial and error, one Hamiltonian circuit is Portland, Boise, Butte, Salt Lake City, Reno, Sacramento, and Portland, which represents a sequence of flights that visits each city and returns to the starting city without visiting any city twice. The weighted graph. A weighted graph is a graph in which each edge is associated with a value called weight. The objective is to find the minimum weight provided all vertices are visited. Now let's consider this graph. What is the minimum possible weight of the graph above? You can pause this video if you need more time to answer the question. Now for our solution, let's start from vertex 0. From vertex 0, you have two options. You can go to vertex 1 or vertex 7. But then, the next thing that we're going to remember is we have to consider the edge that has a lower value of weight. And so, I'm going to take vertex 1 because 4 is less than 8. Now, on vertex 1, I have two options. I can go to vertex 2 or vertex 7. But then, we have to consider the edge which has a lower value of weight. And I'm going to choose vertex 2 because 8 is lower than 11. Now, let's go to vertex 2. In vertex 2, I have three options. I can go to vertex 3, vertex 5, or vertex 8. Although that the two vertices going to vertex 5 or vertex 8 have lower values of their weight, but then I will be missing the chance to go to vertex 3. Again, in our condition, we're going to go to all the vertices in our graph. So this time, I'm going to choose vertex 3. So I will have there an edge which is equal to 7. On vertex 3, I have again two options. I can go to vertex 4 and vertex 5. I will be choosing vertex 4 because the edge is only 9 compared to 14. Now in vertex 4, I only have one option. So that would be going to vertex 5. On vertex 5, although we have there three possible paths, but then I cannot go to vertex 2 or vertex 3. Simply because I have to visit only one vertex once. So I'm going to choose vertex 6. And from vertex 6, I have there two options. I can go to vertex 8 or vertex 7. But then 1 is lower compared to 6. So I'm going to take vertex 7. And lastly, to complete our path, from vertex 7, I can go to vertex 8. Now we have there our complete path. Now computing all the values of our edges, the weighted graph is equal to 58. This time, we're going to know the minimum possible weight of the graph when we consider a Hamiltonian circuit. A Hamiltonian circuit states that we have to go to all of the vertices, but then we have to go back to the point where we have started. You can pause this video if you need more time to answer this question. Now for our solution, I can take this path. So from vertex 0 going to vertex 1, going to vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, vertex 8, vertex 7, and go back to vertex 0. So that would be our path. And the value of the weight is 69. The greedy algorithm. A greedy algorithm, as the name suggests, always makes the choice that seems to be the best at the moment. This means that it makes a locally optimal choice in the hope that this choice will lead to a globally optimal solution. How do you decide which choice is optimal? Assume that you have an objective function that needs to be optimized, either maximized or minimized at a given point. A greedy algorithm makes greedy choices at each step to ensure that the objective function is optimized. The greedy algorithm has only one shot to compute the optimal solution so that it never goes back and reverses that decision. Steps in finding Hamiltonian circuit using the greedy algorithm. First, choose a vertex to start at. Then travel along the connected edge that has the smallest weight. If two or more edges have the same weight, pick any one. Number 2. After arriving at the next vertex, travel along the edge of smallest weight that connects to a vertex not yet visited. Continue this process until you have visited all the vertices. And lastly, return to the starting vertex. Example, use the greedy algorithm to find a Hamiltonian circuit in the weighted graph. A Hamiltonian circuit will always have exactly two edges at each vertex. In step 2, we are warned not to mark an edge that would not allow three edges to meet at one vertex. Begin at A. The weights of the edges from A are 13, 5, 4, 15, and 8. The smallest is 4. So connect A to D. At D, the edges are 8, 7, 2, and 12. The smallest is 2. So we're going to connect D going to B. At B, the edge with the smallest weight is B to F. Connect B to F. At F, the edge with the smallest weight is 7. So it is from F going to D. However, D has already been visited. Now, choose the next smallest weight, edge FE. So connect F to E. At E, the edge with the smallest weight whose vertex has not been visited is C. So connect E to C. All vertices have been visited, so we are at step 3 of the algorithm. We return to the starting vertex by connecting C to A. The Hamiltonian circuit is A, D, B, F, E, C, and A. The weight of the circuit is 4 plus 2 plus 5 plus 10 plus 6 plus 15 is equal to 42. The edge-picking algorithm. The edge-picking algorithm states to mark the edge that has the smallest weight in the complete graph. Then, the edge with the next smallest weight is marked as long as it does not complete a circuit and does not add a third marked edge to a single vertex. This process continues till no longer an edge can be marked. Steps in finding Hamiltonian circuit using the edge-picking algorithm. First, mark the edge of smallest weight in the graph. If two or more edges have the same weight, pick any one. Second, mark the edge of the next smallest weight in the graph, as long as it does not complete a circuit and does not add a third marked edge to a single vertex. And lastly, continue this process until you can no longer mark any edges. Then mark the final edge that completes the Hamiltonian circuit. Now, using the same graph, use the edge-picking algorithm to find a Hamiltonian circuit in the weighted graph. You can pause this video to answer this question. Now for our solution, we first highlight the edge of smallest weight, namely BD with weight 2. The edge of the next smallest weight is AD with weight 4. The next smallest weight is 5, which appears twice with edges AE and FB. So we can mark both of them. So we have here FB and AE. So both have the same 5. There are two edges of weight 6, the next smallest weight. So BC and EC. So both of them have the weight which is equal to 6. We cannot use BC because it would add a third marked edge to vertex B. We mark edge EC. We are now at step 3 of the algorithm. Any edge we mark will either complete a circuit or add a third edge to a vertex. So we mark the final edge to complete the Hamiltonian circuit, edge FC. Beginning at vertex A, the Hamiltonian circuit is A, D, B, F, C, E, and A. In reverse direction, an equivalent circuit is A, E, C, F, B, D, A. The total weight of the circuit is 4 plus 2 plus 5 plus 14 plus 6 plus 5. That is equal to 36. In reverse direction, we have 5 plus 6 plus 14 plus 5 plus 2 plus 4, and that is also equal to 36. Check your progress. So use the greedy algorithm and the edge picking algorithm to find a Hamiltonian circuit for this graph. Thank you so much for listening and watching this video. Please don't forget to like and share this to your friends and your classmates. And if you have questions, just go to the comment section below. And I hope you consider subscribing to this YouTube channel. Again, it's my pleasure to create and make video on your math lessons to make your learning journey a wholesome and fun activity. By the way, this is your Sir O. Till next time, God bless and keep safe always. Goodbye.